from Transcat, and I'll be your moderator this afternoon. Our webinar topic is Why Monitor Electrical Energy and How. The topic is being presented by George Vlahos from AEMC. George is the Eastern Sales Manager of AEMC Instruments, a leading manufacturer of test instruments specializing in power quality, ground resistance, and insulation resistance products. George joined AEMC in 1997. He is responsible for all sales and technical support for 22 states in the United States and 2 provinces in Canada. He's a native of Illinois and began his career in instrument design as an electrical engineer with Copar Corporation located in Oakland, Illinois. After 14 years as a design engineer, he joined Resistive Instruments, specializing in power quality products, and 6 years later moved on to AEMC. George has a BSEE from Illinois Institute of Technology, and he has been an IEEE member for 5 years and a member of the Substation Testing Work Group for IEEE Power and Energy Society. That was a mouthful. We expect the presentation today to last roughly 30 minutes, and we'll answer any questions that have been submitted afterwards. During any time during the presentation, you can send your questions through the question box to the right in your webinar controls. I also wanted to mention that the webinar is being recorded. You will each receive a follow-up email with a link to the recorded webinar and slides of today's presentation. At this time, I'm going to turn the presentation over to George.
Thank you, Nicole, and good afternoon to everybody. As Nicole said, my name is George Vlahos, and I'm with AEMC. We've been involved in electrical testing and specifically in power measurement for over 15 years. And today's presentation is going to introduce you to the basics of it with a help and a bit of an understanding on what's important in the electrical industry for monitoring and how we can monitor that appropriately and properly. As Nicole indicated, any questions you have, feel free to submit through the question pane. As you are all muted for this, I will proceed through the presentation, but can respond if there's something critically important by using the chat function. Otherwise, we will take care of all questions at the end of the presentation. We can start out with a basic understanding of what is electrical energy. And while you all probably have a fair understanding of this, it's just important to emphasize that electrical energy is what powers all our devices, and it is what the utility bills us for as an electrical energy charge. They measure that in something they call watt hours. And this is the use of the energy over time, hence the term watt hours. And this is what actually is the majority of your energy bill is based on, is how much energy you're using from the utility, and depending on the time of day and some other factors, how they do their billing. Electrical energy can be derived from many, many sources. We're all familiar with the basic fossil fuel mechanism that had been around for a long time, as well as the movement to nuclear energy. And in more recent years, we've seen the development of solar, wind, and hydro energy also. Now, there is a bit of a misunderstanding, or sometimes a conceptual understanding, a difference between something called energy and something called power. Both are terms used in the electrical industry, and though they are related, but they are different. Power is measured in watts, and that's the actual instantaneous amount of energy you're drawing off the electrical utility. So when we refer to a 100-watt light bulb, what we're meaning is that when you turn that light bulb on, at the instant you turn it on, it starts drawing 100 watts. And then the power draws over time, and the way we express the use of that power over time is we refer to that as energy, which, as I indicated, is measured in watt hours and is accumulated over time as the usage of energy from the utility occurs. Now, quite simply, if you think of a 100-watt light bulb, at the instant it begins to turn on, it starts drawing that current from the utility. The voltage is present, and when we flip the switch, the element that's inside the incandescent light bulb starts to pass current through it, emits light, and the amount of current that it passes through it can be expressed in terms of the current draw, which is able to be measured in amps of current, or the usage of that energy with the wattage the voltage included in it would be expressed as 100 watts is what the bulb would be drawing in energy. Using 1 amp of current off of a 100-volt source, we would have 100 watts of energy. Now, if that light were to stay on for an hour, the utility would bill us for 100 watt hours. That's how the watt hour calculation works. Oh, you took 100 watts from me, and you took that 100 watts for an hour, you would have 100 watt hours of billing. Now, if the light were only to stay on for a half an hour, although it was drawing 100 watts, at the half hour, if you turned it off at the end of the hour, the utility would bill you for 50 watt hours. Now, the reason I use this example is it's pretty easy to understand that the ability for us to understand where the watt hours come from is all based on and off time of various loads within our facility. If the light's not on, it's not costing me anything. If the light's on, it's costing me something. Now, our electrical system could be thought of in three different modes, three different primary modes. There is what is referred to as a single-phase load. A single-phase load would be something like a light in your facility. And in order to monitor that light, you would need to have a pair of voltage leads that would connect up to both sides of that wire that's going to the lamp. And that would be used to monitor the voltage. And then you would have to have some type of a device, which we call a current transducer, which would wrap around only one of those conductors. And then we would be able to monitor the current and the voltage, and products can then calculate the wattage from the voltage and current being monitored. And that would be characteristic of a single-phase system. And our residential structures are based on a pair of single-phase systems. In our residential structures, we have something that is called a split-phase system. And the split-phase system would use primarily, again, for residential and small commercial facilities. In this case, we would need 3 voltage leads because there are 2 active conductors bringing voltage into your facilities. We refer to those as L1 and L2, and they're both related to the neutral wire, which comes in also. So to properly monitor that, we would need to have 3 wires. We would have 1 wire connected to L1, 1 wire connected to L2, a 3rd wire connected to the neutral, which now allows us to monitor both of those voltages. But then we would need to employ 2 current transducers, 1 on each of those phases, L1 and L2, to monitor the 2 current loads. Proper equipment that's capable of doing this would then bring those leads into the system and display to you the voltage and the current. And if capable, the equipment could then also calculate the wattage being used and display watts, which would be that instantaneous value. Now, in our larger commercial and most of our industrial systems, we're going to use things that are referred to as 3-phase, 3-wire, or 3-phase, 4-wire systems. I don't want to confuse you too much with this. I just want to let you know that in those cases, we would potentially need 3 voltage leads to connect up to the 3 phases, L1, L2, and L3. And we would use a couple CTs to monitor the currents in the 3-phase, 3-wire system. And then if we were in a 3-phase, 4-wire, or sometimes there's also 3-phase, 5-wire, we would need multiple leads to correspond to that as 4 or 5 voltage leads to measure the 3 phases, reference to the neutral, and possible also reference to a ground. And that would give us our voltage monitoring. And then we would need 2 or 3 of these current transducers to be able to properly measure all the currents. The reason I'm explaining this is that this is the complete way to be able to measure power being used by a single-phase, split-phase, or 3-phase load. These would be able to express the instantaneous values of the current and voltage, display in many cases what the wattage is of that is being used by measuring the currents that are also being used on those loads. And this would give us a real-time value, understanding exactly the energy that is being used from a system. We would measure the power and then over time calculate the resulting energy that is being used from that. You might ask the question, why would you want to record this? What's the advantage? What's the benefit? What's the usage of being able to record this type of information? Well, as I indicated earlier, energy is what the utility bills us for. Now, they play variations on that billing. They do incorporate such things as power factor, peak demand, harmonics, and other things that they could, in addition, hit you with charges for. And these are typically called out on your electrical utility bill when they want to indicate to you that they're billing you for more than just the pure wattage being used. What we do know from many years of experience is short of labor costs, typically the secondary most expensive operating cost within a facility tends to be energy usage, primarily electrical energy, but there's also other types of energy used in facilities. Sometimes it's steam power, sometimes it's gas, there's other things being used. But if you look at the bills associated with operating commercial and industrial systems, Energy, it used to be a throwaway cost. It's no longer a throwaway cost. It is a significant portion of the operating cost on a monthly basis or yearly of a facility. From that, you could determine, obviously, if you could lower your energy usage, you could reduce your operating expenses pretty significantly. There are many ways to do this. You can use energy efficient devices. You could turn loads that are currently not being used off. You can understand what the operating cost of a load is and control that operating the time period of that to, for instance, one of the things utilities can bill for is peak demand. And if you turn on all your equipment in the morning when you're in the peak period, you will necessarily see an additional charge. If you could stagger your startup, in a lot of cases, you can actually save some energy. The key thing to draw from all this, though, is you need to know what you're using in order to know what you could curtail to lower your energy cost. You can't use things as simple as just the revenue bill that's coming in from the electrical utility, because that's just telling you what your total facility is, and it doesn't give you any insight into the individual energies being used. Not too many years ago, the state of New Jersey decided that they needed to lower their energy costs of all energy. They put out a mandate that all departments had to reduce their energy cost by 15% within a 1-year period. We were contacted by the people who maintain the parking lots and said, how in the world are we going to be able to reduce our electrical energy or our energy? We don't have that much energy being used. Well, one of the things that we and they both realized is that their parking structures have lighting. And the question is, what can we do with the lighting load? This wasn't as simple as just going in and having a contractor come in and replace the lighting with what they called more energy efficient lighting. The particular group, that department, had to document the usage and the reduction, and they also wanted to prove that, in fact, the lighting was saving the amount they wanted. So they wound up having to do a 30-day recording before doing any relamping, measure the energy usage on the lighting loads, have the company come in and do the relamping, and then do another 30-day recording to see just what they were able to attain after relamping. And it turned out they were pleasantly surprised that they were actually saving around 21% when the contractor only guaranteed them about 15 or 16%. So knowing what their load was, knowing what the effect on it was able to tell them how much energy they actually saved, and as a result, how much they actually saved in operating cost, meeting the demand requirement by the state of New Jersey. Now, I mentioned different types of loads. Let's take a look at those loads visually for just a second. If we look at what a typical single-phase load might be, over on the right-hand side, you're going to see we have some type of source of energy. And again, this could be anything from fossil fuels being burnt to nuclear plants to a solar or a wind farm producing the electrical energy. Typically, that energy will then go through some form of transformation, which is the area shown with the squiggly lines, and it would change the voltage that's coming in to bring it into a voltage that's compatible with the equipment you're trying to use. A utility distributes high voltage because as you increase the voltage for a given load, you will be decreasing the current. So they distribute a higher voltage and then step it down. So it's quite common that in your facility, you may have 110, 220, or 480 loads, but the utility would be bringing you 4160, 12,006, or they might even bring in higher voltages. When they transmit the voltages from city to city or state to state, they use what are referred to as transmission voltages, and those voltages would be up in the 75,000, 100,000, 300,000 range as the voltage is going from one location to another. So it becomes necessary to step that down and bring that into a more usable fashion in a lower voltage, which would be done at transmission substations, then into distribution substations, and then into distribution transformers located along our poles, or if they happen to be pad mounted. Some customers will actually incorporate their own on-site transmission or distribution voltage transformers, where they bring in 12.6 internally into their facility and then step it down to 480 or 240 or 120 within their own facility, having some higher voltages distributed building to building. But a single phase load would then be applied to that. We would have a active conductor we would call L1, for instance, or phase A sometimes it's referred to as, would go through a switching operation, which would be activating the device, in this particular case a motor, and that current, when flowing through the motor, would return back through the neutral back to the transformer, and that loop is what is powering the motor that's here. In order to properly monitor this motor, I would put one lead onto the L1 conductor downstream of the switch. I would put another lead of the instrument onto the neutral. As you might remember, I said we would need two conductors to monitor a single-phase load. Those two would be used to measure the voltage being applied to the motor. I would then attach a current probe anywhere along that L1 line, wrapping it around the conductor. It could be attached anywhere from the transformer all the way to directly at the motor itself, and that would monitor the current flowing into that motor using the information from the current monitoring as well as the voltage that we picked up from the two leads. I would be able to calculate wattage of that motor. Accumulating that over time would give me the watt hours, that is the energy that that motor is drawing. Now, this motor could even be some form of variable speed motor. As long as I'm on the utility side of it, that is the energy being used. I would monitor this upstream of any speed control device and let the speed control device do whatever it needs to do with the motor, because it can no more create or lose any energy. It has to take everything coming off the utility and feed it into the customer, and I can monitor it upstream of that device very easily. More commonly used would not be a single-phase system. It would typically be a split-phase system. In this particular case, the transformer is now shown kind of to the left of this drawing. The transformer has the ability to have 120 volts from either phase to the center of the transformer. We typically would attach our neutral wire to the center of the transformer, and I would monitor 120 volts from either phase. We're not going to get into exactly how this works, but these two phases would be opposing each other. They would be 180 degrees apart, and as a result, we would have 240 across the transformer, or two individual 120 volt sources that are out of phase with each other. You would put the single phase loads, things like fans and or lights, across either phase to the neutral by attaching the fan to L2 and the light to L1. I'm kind of balancing my load. If I could, and there's no reason I couldn't do this, I could put both the light and the fan on phase 2 or phase 1, but the result of it would be I could be loading one line more than the other, and it's beneficial to have the loads being balanced as much as possible. We do also have in residential and small commercial 240 volt loads, things like water heaters, ovens, and other type of equipment would be monitored or be operated off of 240 volts. So in this particular case, we would bring the L1 and the L2 to the load. That load would then be powered by 240 volts. Some also bring the neutral. It is not required. You can actually have a 240 volt load running off of two conductors and no neutral present. Now, to monitor the three items that are on this screen, I would connect voltage leads up to L1 and L2 and connect the third lead up to the neutral. I would then put two CTs, one around L1 and one around L2, and that would allow me to measure all three loads being run off this transformer. If I wanted to measure only a given load of this, I could leave the voltage lead where it's at, but I would move the CT so that it's only on the wire feeding the lamp, or it's only on the wire feeding the fan, and I would not be measuring any current going to the hot water heater. I would only be picking up the individual loads. So to monitor properly, the placement of the CT becomes very important. Where do I pick up the current? Am I picking up the current to all loads? Am I picking up the current only to one load or one group of loads? In an industrial environment, it would be very common to have a three-phase system, which is demonstrated on this picture. Now, three-phase systems look more complicated, but they're basically add-ons to the two-phase, split-phase type systems that exist. In a three-phase system, there would be three energy sources and possibly a neutral. If you look at the picture of the cabinet on the left, the black, red, and blue are phase conductors that we would identify as L1, L2, L3, or phase 1, phase 2, phase 3, or A, B, and C. And then the white wire is the neutral that would be used in this system. And depending on whether you have a delta or a Y type feeding system to your facility, this gets to be more the semantics of the operation and not so much with the monitoring of the operation on how the wiring occurs in the facility. To monitor these loads, I would put three voltage leads, one on each phase, If I had a neutral present, I would provide the fourth lead. In the case here, this would be the white wire. I would connect up to that, and that allows me to measure all voltages feeding into this panel. I then would have the ability to put CTs either around the three conductors. The black, the red, and the blue could each have a CT put around them, which would measure the current going into this entire panel, where I would not be able to segregate what is being fed to any load. Or I could leave the voltage leads connected where I told you to put them on the red, black, and blue wires and the white wire, and move the CTs to the individual conductors on the individual breakers. And by putting the CT around the individual conductor, I would only be measuring the load of that particular, I would measure the current going to that particular load, not measuring the entire panel, but actually looking individually at individual parts of the loads on this particular panel. The drawing at the bottom is showing you how the three-phase representation works in the electrical industry. In order for this system to work, these three phases peak at different times, and equipment being hooked up to do this type of monitoring needs to be three-phase aware. It needs to know how to measure these currents properly to be able to pull them off the system and measure the loads being applied to this particular panel for energy purposes. Again, I'm not going to cover this in detail at this point. If you would like additional information on some of these next couple of slides, feel free to contact us for more specific information. But in the industry, the measures that we do of electrical energy can be thought of as watts, VARs, and VA, as shown on this drawing or this picture. The watts are the volts times the amps, as I mentioned it to you. But that's assuming that the load that's being applied to this system is referred to as a resistive load. And in a resistive load, all we have to do, such like an incandescent light bulb, is multiply the instantaneous voltage times the instantaneous current, and we calculate watts. If it is a resistive load, we would also call that VA. As soon as we apply a orientated load, a load that does not have the voltage and current being drawn at the same time, these devices would cause a difference in the measurement capabilities. And in order to measure the actual wattage, which is the expression of energy, we would have to measure volts times amps. We would have to measure the phase angle, sometimes called the power factor, between the voltage and current, and that would go into the calculation. By way of example, if we had a incandescent bulb, which is a purely resistive load, the cosine of theta would be 0, the cosine of 0 is 1. We would have 1 times amps times volts, and as a result, we would wind up with VA and watts being equal. Now, VARs are the hardest one to describe in the industry. They're the portion of the system that we call reactive power, and the reactive power is the kind of almost the opposite of the real power. This is the part that doesn't do any work, but has to be present in order for the work to be done. And to calculate the VARs, we use the volts times the amps times the sine of theta, the angle between the voltage and the current, or the power factor of the system, and that would give us our VAR loading. You don't need to know these particular things to monitor energy usage, but it does demonstrate that we have to monitor the energy in different ways, depending on whether we are monitoring something that is called a resistive load or something that is not a resistive load. When we have a purely resistive load, and again, the example of this would be something like an incandescent light, what we have is theta is 0 degrees. That means for every instantaneous change in the voltage, the current tracks it exactly, and as a result, the watts and the VA are equal to each other because the degree angle between the two is 0, and as a result, or is the degree angle 0, and the cosine of 0 is 1, and as a result, we have watts equaling VA. In the industrial side, you would find people referring to this as something having a power factor of 1, which is a very desirable thing. If you have a power factor of 1, your electrical utility can deliver you all the energy you need without any problems, and theoretically, they would love that. And all energy being used is immediately converted to work being done. The motor turns, the light turns on, things happen as a result of this with no loss in energy. Now, that is not quite true when you have other types of loads being applied to your system. When you apply things like motors to your electrical system, the motor does not draw current at the same exact instant as the voltage changes. And in fact, there is a phase angle between the motor's voltage and the motor current, meaning that theta increases from 0, that of a resistive load. It could, but it never does, increase to as much as a value of 90. And as theta goes up, what we find out is the VA will drop. I'm sorry, the watts will drop while the VA remains constant. This is a load that we typically refer to in the industry as a lagging load, which is what a motor provides because a motor is inductive. And as a result, the current and the voltage are not in phase. We say the load is lagging because the current lags the voltage. And as a result, we have something called power factor. In many areas of the country, utilities bill you for the power factor as an increased charge. The rationale behind it is the fact that if you didn't bill for the power factor, people who had more motor loads would be paying less in energy than people who had a purely resistive load. So they have VAR compensating meters that are used in the industry to compensate, it's specifically used in the industrial sector, as you apply those motor loads to properly bill you. They have a power factor penalty, which they would charge you. They wouldn't look at the power factor of an individual load. They would look at the power factor of your facility, and as a result, bill you for the use of energy in an inductive fashion, which costs them more to produce than in fact you're using. The opposite of a motor load or an inductive load is a capacitive load. These loads would be associated with more like things like computers. Computers produce a different waveform arrangement. They still have the angle between the voltage and the current increasing from 0 to probably again as much as 90, but it never actually makes 90. What you'll find out is, again, as you increase theta, the value of wattage drops while the VAs remain the same. And as I indicated in the previous slide, to the opposite side here, though, as theta increases capacitively, we see increasing VARs in a capacitive sense, and this is called a leading situation where the current leads the voltage and would have a leading power factor. Leading power factor is even more difficult for utilities to overcome, and again, they would have the potential ability to bill you for that. Now, it's not too common in the industry in the past. If you had an inductive load with a lot of motors, either you might in your facility have something referred to as a capacitor bank that is supposedly put in there to help you, or the utility would hang capacitors on the distribution lines coming to your facility. And they're done specifically to try to offset the VAR loading that your facility would present. And if these capacitors are working properly, they would only offset as much inductive load as you were putting onto the system, and we would never lead to this situation of a leading due to those capacitive loading. On the other hand, things like computers don't really much care about what else is going on in a facility, and they do have a leading current, and that leading current does produce a power factor that is in a leading fashion, again, requiring energy, but not actually converting that energy over to the type of work you need it to be able to do. This is a little bit of the background of the idea of loading. I don't want to cover any more of this right now, just to let you know that we have in the industry resistive, capacitive, and inductive loads, and those loads are what the utilities are providing us the energy for, and we have to be able to use that in an intelligent fashion, reducing our energy usage to save money. Something that can help remember those two terms I just showed you is something the electrical industry has used for years called Eli the Iceman. Eli the Iceman is a way to remember inductive and capacitive loading. If you look at the ELI, what that means is the E is representative of voltage, and you'll see that the voltage leads the current, and then the Iceman one is the current is capacitive, and it is occurring before the energy. So the I is before the C, where in the other one, the I is after the L. So the I lags in the inductive load, the I leads in the current load, or the capacitive loading. And this is just the way the industry is a shorthand way of remembering what happens in electrical systems as you apply inductive and capacitive loading. Understand these are the only types of loads you can apply to a utility, either a purely resistive load, such as an incandescent light bulb, or motors, which would be inductive in nature, or computers, which would be capacitive in nature, and that's how we load our electrical systems. Saving those, reducing those loads is what can save us energy. Now, there are many different type devices available in the industry to monitor and do this kind of measurement. The simplest type devices you're going to run into are going to be handheld devices, which could be used to measure one voltage and possibly one current. These might be like a multimeter, would be capable of measuring the voltage. You could put the two leads across a phase, and you'd be looking at the instantaneous providing of voltage to a load. Some of those devices allow you to add an option to it, which is a current probe. And by attaching the current probe to the meter, you could put the current probe around the conductor, and you'd be able to monitor the current flowing to the load. In both of these cases, these things are instantaneous values. Some meters will allow you to look at the instantaneous wattage and actually calculate the instantaneous wattage for measuring the instantaneous current and voltage. But really, if you want to get the real picture of what's going on, you can't use these types of devices to look at the energy being used. That's strictly the power which is being led instantaneously. To really be able to measure the full system, what you really need is a device capable of measuring all three voltages simultaneously and all three currents simultaneously, and be able to gather and store that information internally. Now, one of the important things about this type of measurement is you have to make sure the devices you're using are called true RMS devices. The term RMS means root mean square. It's just a way we express the 120 volts that you might be familiar with. That 120 volt signal actually ramps up to about 170 volts, comes down through zero, goes back to minus 170 volts, and comes back to zero. And we somehow call that 120. Well, the way we do that is we do a calculation called a root mean square on that sinusoidal wave, and we can come up with the 120 volt RMS value. If I'm sampling that waveform, which is occurring 60 times a second, by the way, if I'm sampling that fast enough so that I'm picking up all the points on the waveform, the product is called a true RMS meter. The reason we specify that is that there are other devices in the industry that do not look at it quick enough, miss some of the things going on during the fluctuation of the voltages or currents, and express misleading values. Those devices would be known as averaging products, or products that don't identify themselves as true RMS. So if you're doing this type of measurements, it's critical that you use an instrument capable of reading quick enough to pick up the actual values of voltage and current going on. Now, typically to do this type of recording over time in order to calculate the energy, you would have to have memory in the instrument. It would have to be capable of recording this information and giving it back to you at a subsequent time, telling you how much was being used instantaneously, which is, again, the power, but then looking at the energy usage over time, which would be the watt hours of information, or var hours or VA hours. It's very common in these products to actually incorporate a real-time clock to record the time of day, because if you're trying to do energy monitoring and you want to know where your energies are being used, it would be beneficial if you see a spike in energy to be able to associate that with a certain time of day to find out why that energy is spiking at that particular time of day. AEMC does produce a couple products that are capable of doing this thing, and while this is not intended to be sales, this is intended to be a technical presentation. Just want to give you a look at a couple of the products. The product on the left is referred to as a power pad. It's a model 8336. He brings in all three voltages, including neutral and ground voltage connections, as well as four currents, the three phase currents plus the neutral current, and does what is referred to as a power quality study. This one looks at waveforms and everything else in addition to the energy. For those people who are only interested, by the way, it does things like harmonics, and it does transient detection and a few other things. The one on the right is referred to as a power and energy logger. This guy is designed to primarily measure watts, vars, and VA, and measure that energy over time, doing the watt hours, the var hours, and the VA hours. Both of the products incorporate memory for you to be able to store the information for typically 30 to 60 days worth of recording data. The products come complete with all the CTs and voltage leads necessary to monitor it. The product on the right is the product that the state of New Jersey used to monitor the lighting loads in the parking lot structures. Features you'd find in the products is how many different power configurations they incorporate. Not everybody's power is provided to them in the same means, and you have to have the ability for the instrument to be configured to the type of power. The PAL incorporates 17 power configurations built into the unit. The power pad that we have, the 8336, you can program an infinite number of configurations, but there are no standard configurations pre-programmed in the instrument, except 3-wire and 4-wire configurations. We incorporate memory in these units, expandable up to 32 gig in the case of the PEL. So this thing could actually record for months and months and months before downloading. It also incorporates communication capabilities, Ethernet and Bluetooth, to transfer the data either real time or after the recording is done. And it's quite common to record watts, vars, and VA, as well as the watt hours, the var hours, and the VA hours of a load. And you would then generate a graphical result of that data. Typical outputs could be anything from a screen capture of a waveform to harmonic information to graphs of energy over time. A very typical graph might look something like this. This would be a watt-hour graph that was being accumulated. You could see kilowatts on the left-hand side is a kW, and you could see the timestamp of 1 division per day across the bottom. And the 3 lower graphs, the red and the blue, and there's a black built in there, it's a little hard for you to be able to see, represent the individual phase loading, and the gold represents the total energy accumulation. You would be able to look at this. This is a short one over a 7-day recording. Indicated in the middle, it says this was a 7-day recording with 1 day per division, starting at 1 p.m. on the 2nd and going through 1 p.m. on the 9th. This is a very simple appearance of a graph. There's many more data points you could bring out, but this might be one just to let you highlight and look at where your energy peaked. In this case, I could see peaks over 25 kilowatts up to 32, and in one case it went all the way up to 37 or 38 kilowatts being drawn on this particular load. By graphing it in this way or accumulating the data and then presenting the graph, it gives me the ability to look into the energy usage and make decisions on how I might be able to reduce or regulate the energy usage within a facility. From the point of view of reporting systems, you can also generate tabular reports that would actually document the energy information, telling you how many megawatt hours in this particular case were being used. And this could be used to relate to your energy bill. The PEL product even incorporates an ability where you can put in your energy cost in cents per kilowatt hour, even if you have multiple billing periods during the day, and it can actually give you the dollar value of the energy usage expressed in actual US dollars of energy usage. Now, AEMC is supplied through Transcat. Nicole is the person that's the main contact with us at the Transcat location. If you're interested in getting more information, if you need to get clarification on anything that was being said in here, or you want to know more information, you can contact Transcat and they can put you in contact with myself or anybody at AEMC. We also have an 800 number. Transcat has their 800 number. We also have an 800 number for our technical support available on our website, AEMC.com. At this point, I'm going to turn this back over to Nicole. I believe you've joined us. And Nicole, if you would take care of the question portion.
Yep. All right, thanks, George. So that does conclude our presentation portion of the webinar, and we're now going to move into the Q&A session. So if you'd like to submit questions, as a reminder, you can send it through the question box in your webinar controls. I do have a few to get us started that came through a little while ago. First one, what is a load profile? What does it look like and what does it tell you? How do you use it?
Okay, good question. The last picture I showed you, the last graph I showed you, is actually a load profile. This is a profile of a given load over time. And what we could determine from it is the variation in the load relative to the load, to the time of day. This particular case, if you look at the time gradient, this is not zoomed in, but if I was going to do an actual load profile in this particular motor or building, I would probably zoom into 1-day periods. I would be able to zoom in on this graph so that the left-hand side was the beginning of a day and the right-hand side was the 24 hours later. And I would look at that profile over time. What a load profile means is representing load over time. That's the term profile. From that profile, there are several things I could determine. I could determine whether or not the load is consistent, whether it's changing or fluctuating on a regular basis. I'd be able to look at the variation in that load and see how much it's varying from one side to another. That load profile could also be used in conjunction with other information, such as if the load profile was off of a motor running a pump, I could also look at the volume that that pump pumped, and I could express and compare that to the load profile, and it would tell me or give me insight into how that motor was performing that load operation I was looking to do, such as is the motor drawing way more current than it should when the motor's 50% or 70% loaded, which can happen on motors that are getting older, or other things in a similar nature relative to a load profile. It's merely, the term load profile is merely how do I express energy usage over a time basis and be able to graph it and be able to reuse that. Hope that answers that question, Nicole. If it doesn't, they can certainly follow up.
Sure. Okay, the next one. Why is power factor so important?
Well, that's actually a little easier one to answer. The simplest reason why power factor is important is you may be getting billed for it, and the worse your power factor is, the more you get billed. So there is a benefit in understanding what your total power factor is for your facility and what the power factor of individual loads are, if for no other reason, just to understand what energy cost there is associated with that power factor. The unity power factor is the ideal situation. The utility does not have to do anything extra to produce your energy. Anytime you move away from unity, the utility has to do more work to produce your energy for you. And the way they measure that is with power factor. There's a lot of locations where if you're below a 0.95, you get a charge or a fee added on to every kilowatt you use. Other places I've heard 0.88. You can do things to correct your power factor through loading and adding of capacitor banks. Reducing the power factor directly reduces your load cost, but you cannot know that without measuring power factor real time. Again, Nicole, hope that answers that.
Okay. Does the utility bill residential customers the same way they bill commercial or industrial customers?
They absolutely do not bill them the same way. Residential customers are billed on a pure wattage usage. Watt hours are what you get billed for. The meter that they attach on the back of your house is not compensating for anything else. It's measuring the instantaneous energy and accumulating that, and you're getting billed purely on the watts being used. In an industrial or larger commercial sectors, they will use a different form of metering, anything from what is called a VAR compensating meter to other techniques, and they will bill you for additional things other than the energy usage. You could succumb to a peak charge. You could succumb to a power factor charge. There's even discussion in the industry about billing you if your facility is generating harmonics. All this occurs in the industrial and the commercial sector, does not occur in the residential sector. So if you're doing residential monitoring, you could do a lot less to understand. You have to do a lot less to understand your energy bill. When you're in the commercial or industrial sector, you have to do significantly more to understand your electrical energy bill.
Okay, what is meant by true RMS?
I described that a little bit in the presentation, but just to go back over it again, when the utility generates a voltage, they generate a very, very pure sine wave. That sine wave is then delivered to your loads, and our loads are the cause of distortion. As the load draws from the source, it can distort the incoming source because it's loading of the transformer coming in. If we distort the waveform, the measurement of its energy has to be done with a much higher sampling. We have to be able to measure the distortion and take that into calculation when we're calculating energy. If I'm not using a device that is true RMS, it is not capable of picking up those fluctuations and will therefore misrepresent the value. So in power and power quality systems, it's important and critical that the device you're using is a true RMS measuring device to give you the real values and not representing the misrepresentation in those values. Thank you, Nicole.
Thanks. One more, unless we get another one that comes in. Why does my building have a capacitor bank?
I touched a little bit on that in the presentation also. The main purpose of a capacitor bank in a facility is to try to offset the motor loading that's in your facility. The capacitor bank is a leading power factor device. The motors are a lagging power factor device. And if I can incorporate a capacitor bank, in a lot of cases, I can offset the losses associated with the lagging of the motor power factor by applying capacitance to it. And applying the capacitance causes the power factor to move more toward the one that the utility likes. The problem is if that capacitor bank is not working properly and stays on, for instance, all the time, when your motor turns off, you create a leading power factor, which is just as bad as the lagging power factor. So capacitor banks are typically either sized way under the total load allowing for some power factor to still exist under full operation, but compensating for lighter operation, or they're dynamic, which allows them to add or subtract capacitance as the loads in the facility change. In many instances, we have found these capacitor banks were installed years ago, not checked, and as a result found out they were misoperating, actually costing the customer money instead of saving the customer money, which is the purpose of the capacitor bank that is installed in an industrial sector. Again, I hope that answers the question.
Okay, so that looks like that's it for questions, and it concludes our time for today. If you do have further questions that weren't answered during the presentation, you can feel free to reach out to me at nvanwert@transcat.com. You can always go to our website at transcat.com or call our 800 number, 800-828-1470. Thanks for joining us today. We hope you got something out of the presentation. Oh, again, we will follow up with the links to the recorded webinar in a few days. And we hope that you continue to join us for future Transcat e-learning webinars. And happy holidays, everyone.
I'd like to add my thanks also. Appreciate it very much.
Take care, George. Thank you.
Thank you. Bye.
Bye.